Hi, my name is Tariq Al-Turkestani, and today I'm going to present our paper Maximizing I/O Bandwidth for Reverse Time Migration on Heterogeneous Large-Scale Systems. This research has been done in collaboration with Dr. Hatem Lataif and Professor David Keys from the Extreme Computing Research Center at the King Abdullah University of Science and Technology in Thuwal, Saudi Arabia. In our research, we implement a multi-level generalization of traditional two-level memory systems, one fast but small, the other large but slow, processing asynchronous prefetch and write back. Our implementation can accommodate more than 2 layers of memory and storage, and it dedicates a small number of available threads as I/O helpers. It also coordinates between levels of memory to minimize the size of buffers required. For a representative I/O-bound application, seismic inversion, we significantly outperform state-of-the-art provided solutions. On a Cray XC40 supercomputer, Shaheen 2 at KAUST, which is currently ranked number 45 on the top 500 list, our proposed solution, MLBS, outperforms state-of-the-art parallel file systems as shown in a recently published paper. On the IBM-built Summit supercomputer, which is currently ranked number 2 on the top 500 list, using 2,048 compute nodes equipped with a total of 12,288 GPUs, MLBS achieves up to 1.4x performance speedup compared to the reference parallel file system-based implementation. MLBS is also demonstrated in cosmology, particle-in-cell combustion applications, and a classical out-of-core linear algebra kernel Shulatsky decomposition. In this talk, I'll define the problem, motivate our research, introduce our proposed solution and principal application, discuss some of the experimentations and the results, and I'll finally conclude with a summary and a future work statement. As we all know, there's a growing performance gap between processing units and storage systems. Asynchronous system calls do not hide the I/O overhead, mainly because of the limited buffer sizes. Blocking for I/O may amount for up to 95% of the entire wall time. We consider a major application driving supercomputer acquisitions. We could also see similar reports of more than 50% of wall time arise from climate and weather modeling applications. Iterative applications such as reverse time migration write or read a huge amount of intermediate data at predetermined time steps. When a call to a write or read is invoked, the I/O library copies the data between the application space and the I/O library space. We have tracked the timeline for a seismic inversion application, and we have seen that the I/O library could sometimes be a bottleneck, causing the application to block waiting for the data to be flushed from the I/O library to the storage system. New HPC systems are equipped with hierarchical storage. We have supercomputers that are equipped with the remote shared bus buffer, and we have supercomputers that are equipped with node local bus buffers. We have also supercomputers that host compute nodes that have access to GPUs with high bandwidth memory. Now, let's look at an application that computes on a GPU and outputs to disk a huge amount of intermediate data in a form of a snapshot. The computation will start from the GPU, and at a predetermined time steps, a checkpoint of the entire state or grid would be taken and it will be copied to the CPU. And from the CPU, it will be flushed to the parallel file system. This process will be repeated for the entire execution time of this given application. Now, this same application may require to read back all of these snapshots for further processing. The CPU would then prefetch these blocks or snapshots and load them to the GPU. And it will do so for the entire snapshots that have been dumped to disk. The goal of my research is to overlap I/O or compute through continuous pushing and pulling of all of the intermediate snapshots through and across all of the intermediate storage layers without stopping the computation. And in the case of reverse time migration, and as you see in this timeline, we want the computation and the I/O to be happening in parallel without affecting one another. Recently, we have proposed a multilayer buffer system, MLBS. MLBS utilizes all of the available memory and storage layers in a given system in order to overlap I/O and compute for the applications that use it. MLBS consists of two building blocks. One, a very simple set of APIs, write and read, and two, decentralized helper engines that help to prefetch and write back all of the data in all of the memory layers. The write API of MLBS copies the data in parallel from the application space to the MLBS space. Once the copy is done, then the application could continue computing while the MLBS helper engines move the data across all of the intermediate layers. The read call of MLBS is then as simple as a pointer swap. And the goal of the helper engines of MLBS are to order the storage and memory layers from fastest to slowest, to move the data between the application space and MLBS space, to conduct the actual write and read operations on memory and disks, to move the data between the layers, to cache in and out the data based on the data access patterns, and to ensure the separation of I/O and computation tasks. We have integrated MLBS into reverse time migration, vector particle in cell, hardware accelerated cosmology code, Kaust adaptive reacting flows solver, general matrix multiplication, and Cholesky matrix decomposition. And in this paper, we're going to focus on reverse time migration. Reverse time migration, RTM, is preferred for modeling and imaging seismic data in areas of complex wave phenomena. Unlike one-way wave equation migration, RTM is the most advanced seismic imaging technique for decision support on drilling investments. The economic value of oil reserves that require RTM to be localized is in the order of tens of trillions of dollars. RTM requires fast computational power. Oil and gas companies such as Saudi Aramco, Total, Eni invest heavily into supercomputers. A significant portion of the time in RTM is spent in disk I/O. Therefore, our research has a direct impact on the P&Ls of these oil and gas companies. RTM requires combining at regular time steps a forward propagated source wave field with a back propagated receiver wave field. In the first phase, the 3D simulation states or snapshots of the source wave fields are computed and saved to disk at a predetermined time steps. In a second phase, the receiver wave field is computed and the imaging time steps along with the source snapshots are retrieved and correlated with the receiver snapshots to update the final image. We have experimented the scalability of MLBS and RTM on two powerful supercomputers, Summit and Shaheen. Summit is an IBM-built supercomputer with more than 4,000 compute nodes, where each compute node consists of 6 GPUs and a node local burst buffer. Shaheen, on the other hand, is a Cray-based supercomputer with more than 6,000 compute nodes and a remote shared burst buffer. Summit is ranked number 2 on top 500 most powerful supercomputers, and Shaheen is ranked number 45 on the same list. Our first experiment was done on Shaheen supercomputer. We used a CPU-based RTM code. We fixed the number of time steps to 3000 time steps, and we fixed the grid size to 800 cubed per shot per node, and we've conducted an I/O at every 10 iterations. We measured write and read aggregated throughputs in gigabytes per second, and we increased the number of nodes from 1 all the way up to 2048 nodes. The scales you see on the axes are on log scale. On the blue curve, you'll see the I/O performance as seen by the RTM app using Lustre file system. And on the dashed blue curve, you'll see the I/O performance as seen by the RTM app using MLBS. In the forward phase, the write phase, you'll notice that especially when we have a small number of nodes, MLBS can speed up the application or the write performance by almost 32 times. And as we increase the number of nodes, that speedup reduces to 3.5x when we have 2000 compute nodes. In the backward phase, you'll notice that MLBS was able to always prefetch the data and have it ready upon request whenever the RTM application needed it. Our second experiment was done on Summit supercomputer. This time we used a GPU-based RTM code. We fixed the number of time steps to 3000 time steps. We also fixed the grid size to 700 cubed per shot per GPU, and we've conducted an I/O at every 10 iterations. Remember, on Summit, every node consists of 6 GPUs. So when we have one node, that would mean that we would have 6 GPUs solving 6 independent shots. We've measured write and read throughputs in gigabytes per second, and we've increased the number of nodes from 1 all the way up to 2048 nodes, or 12,000 GPUs. On the blue curve, you'll see the I/O performance as seen by the RTM app when using the IBM parallel file system. The dashed blue curve shows the I/O performance as seen by the RTM app when using MLBS. On the right, or the forward propagation phase, you'll notice that MLBS can speed up the write operation by up to 3.8x, especially when using small number of nodes. The performance performance gain could be up to 1.4x when using 2000 compute nodes. However, on the read, the performance speed up of MLBS could be up to 1.9x when we have a very small number of nodes, and it could go all the way up to 18x speed up when we have a large number of compute nodes. Few things to note about Summit supercomputer. One is that the machine is equipped with a node local bus buffer, meaning that when an application is running on a node, only the application has access to that bus buffer. Therefore, the performance of the bus buffer does not really depend on the number of applications or number of nodes that are being used on the machine. Two, that writing to the bus buffer could bring you more I/O throughput, especially when we have more than 1000 compute nodes trying to write to the parallel file system. Three, reading from the bus buffer starts to make sense when we have 32 or more compute nodes trying to read from the parallel file system. MLBS's autotoner could see or measure the performance differences between the layers and could make a decision at 1000 compute node to change the order of the layers in order to increase the bandwidth for the application and to achieve up to 18x speed up on read. And finally, on Summit, we reduced the grid size to the point that all of the intermediate snapshots could actually fit in one GPU's high bandwidth memory. And as you could see on your left plot, we were able to have the application or the RTM instant work as if there was no I/O at all and achieve up to 3.27 wall time speed up. And then we increased the size of the grid a little bit to the point that some of the, or at least half of the grids, half of the intermediate snapshots had to be evicted from the GPU to the other layers, whether it's burst buffer or high bandwidth memory, and we were able to achieve up to 3.25x wall time speed up. And as you have seen, using a technique like this, where we utilize the high bandwidth memory as an intermediate storage layer, we could potentially speed up quite a lot of number of applications, especially now that the sizes or the capacity of high bandwidth memories for the new HPC systems or the new GPUs is increasing. And to summarize our contribution on this paper, we've extended our multi-layer buffer system that could continuously push the data up and down and across all the hierarchical storage systems to include the high bandwidth memory of GPUs. We've designed an online autotuner that could help MLBS to monitor and reorder different storage layers based on their sustained I/O bandwidth. We've evaluated MLBS's scalability on homogeneous system, Shaheen 2, and heterogeneous system, Summit, and we've used up to 2048 compute nodes. We've also evaluated the benefit of using high bandwidth memory layer of MLBS as an independent layer and the only layer to store the intermediate snapshots of a small case of RTM. And finally, as a future work, and since we've seen that write and read operations could act very differently on different mediums or different layers, we are going to enable MLBS to have two different independent paths for write and for read. We are also going to integrate MLBS with more GPU-based out-of-core linear algebra routines, since they require a lot of movement of blocks between the GPU and the CPU. And we are going to enable a dynamic scheduler for the MLBS helpers to enable them to prefetch and to write back data based on the online access patterns. With that, I would like to thank you, and I welcome any questions that you might have.